A bearing is a machine element that enables smooth, low-friction motion between two moving parts. It supports a load while allowing relative motion, converting sliding friction into rolling friction. Bearings are so fundamental that the Bronze Age wheel used a primitive bearing, a hole in a cart rotating around a fixed axle. Today, a single wind turbine contains over 200 bearings, and an aircraft engine has over 60. Without bearings, nothing with moving parts would work for long, motors would seize, wheels would grind, and every rotating shaft would weld itself to its housing within minutes. Bearings come in many forms, each suited to a different job. Let's explore all 7 types. The deep groove ball bearing is the most common. Simple, versatile, handles both radial and axial loads. Cylindrical roller bearings replace balls with cylinders for much higher radial load capacity, line contact instead of point contact. Needle roller bearings use very thin, long rollers to fit in tight spaces while carrying heavy loads. Tapered roller bearings can handle massive combined radial and axial loads. You'll find them in car wheel hubs. Angular contact ball bearings are designed for high-speed combined loads. The contact angle determines how much axial load they can take. Spherical roller bearings are self-aligning, ideal for shafts that deflect under heavy loads. And thrust bearings are purpose-built for pure axial loads, like supporting a vertical shaft in a hydroelectric turbine. Each bearing type has a unique load profile. Radial capacity on the x-axis, axial on the y. Deep groove sits mid both axes, the balanced all-rounder. Cylindrical and needle rollers push far-right radial load specialists. Thrust bearings climb high on the axial axis, pure thrust power. Tapered rollers reach top right, massive radial and axial capacity. Every bearing has a precise anatomy. Let us take it apart and put it back together. First, the outer race lifts off. The stationary ring, fixed to the housing. It never moves. Next, the inner race drops out. It mounts directly on the shaft and rotates with it. The rolling elements, balls or rollers, are the heart of the bearing. Each ball makes contact with both races and carries the load. And the cage, the separator, keeps the balls evenly spaced so they never touch. Take every part apart, and the anatomy becomes clear. Bore diameter, D, is the inner diameter of the inner race, the critical dimension that matches your shaft. Outer diameter, D's the overall bearing size. Width, B, is the thickness. These 3 define the bearing number. Radial internal clearance is the tiny gap between ball and raceway measured in microns. Too little causes binding. Too much causes vibration. The contact angle determines how load flows through the bearing, from inner race through the ball to the outer race. Shoulder height on the inner race keeps the rolling elements in place. Every dimension is precisely engineered. The load path, from shaft to inner race to through the ball to outer race to housing. The top ball carries the most load. A ball bearing works by converting sliding friction into rolling friction. When the inner race rotates, friction makes the balls roll in the groove between the races. Each ball rolls around its own center as it orbits the shaft. A glowing tracking dot makes the rotation visible. The cage ensures the balls keep equal spacing and don't collide. It rotates at about 40% of shaft speed. Each ball makes point contact with both races, a tiny elliptical area called the Hertzian contact patch. The pressure here reaches 2 to 4 gigapascals. That's the weight of a car on a pinhead. The material deforms microscopically, shown here exaggerated 1,000, to distribute this immense force. The load is distributed across multiple balls, but not equally. The top ball carries the most force, side balls carry less, bottom balls carry 0. As the bearing rotates, each ball cycles through the load zone. The coefficient of friction is 0.001 to 0.005. That's 100 to 400 less than sliding. When a ball is not enough, bring in a roller. Roller bearings replace point contact with line contact. The rolling element touches the races along the line rather than a single point. This dramatically increases load capacity because the load is spread over a much larger area. A cylindrical roller bearing handles 2 to 3 times the radial load of a ball bearing of the same size. But roller bearings have their own challenges. Edge stress occurs at the roller ends where pressure concentrates. Modern rollers have a logarithmic crown profile to distribute this stress evenly. Rollers also generate more friction than balls, due to larger contact area and sliding from roller end flange contact. Line contact carries more load, but also more friction. Needle rollers take line contact to the extreme. Very thin, very long rollers pack maximum load capacity into minimum radial space. Bearings must handle 3 types of loads. A radial load acts perpendicular to the shaft, like the weight of a gear hanging from the shaft, pushing straight down. Watch the top ball take the squeeze. An axial load, also called thrust, acts parallel to the shaft, like a propeller pushing along the shaft. Watch the balls slide sideways in their raceways, pressing against the shoulders. Many applications combine both. A bevel gear pushes in 2 directions at once, so the bearing feels a diagonal resultant, the vector sum of the radial and axial forces. Angular contact ball bearings and tapered roller bearings are specifically designed for combined loads. The contact angle decides how much axial load a bearing can take. Compare 15, 25, and 40. The steeper the angle, the more the load path tilts away from the radial line and engages the race shoulder. Higher axial capacity, but lower radial capacity. Lubrication is the single most important factor in bearing life. The lubricant forms a thin film that separates the rolling elements from the raceways, preventing metal-to-metal contact. The film thickness ratio, lambda, defines 3 regimes. In boundary lubrication, surfaces touch through the film, high wear, but unavoidable at very low speeds. In mixed lubrication, the film only partially separates them. Most bearings operate here during startup. Some asperities still touch. In full film EHL, elastohydrodynamic lubrication, the oil film completely separates the surfaces. The pressure in the contact zone is so high, up to 3 gigapascals, that the oil temporarily solidifies into a glass-like state. At the inlet, oil is dragged in and pressure builds. At the contact center, the film is thinnest and pressure peaks. At the exit, pressure drops, forming tiny cavitation bubbles. Grease is the most common lubricant. About 90% of bearings are grease lubricated. Oil is used for high speeds or where heat dissipation is critical. And in vacuum or extreme temperatures, solid lubricants like molybdenum disulfide take over, where oils would evaporate or freeze. Bearings are precision components, and they need protection. 3 levels: open, shielded, sealed. Open bearings have no protection. They rely on the machine's own lubrication system. Shielded bearings have a metal plate on one or both sides. The shield blocks large debris, but allows lubricant to flow through a small gap. Sealed bearings have a rubber lip that contacts the inner race. Much better protection, but it generates some friction. The IP rating system: open is IPOX, shielded is IP4X, sealed can be IP6X. More protection costs more friction. Contact seals have a lip that drags on the inner race. Better sealing, more friction. Non-contact seals use a tiny labyrinth gap, less friction, slightly less sealing. The lip rides on a microscopic oil film, essential for seal life. Without it, the seal wears in minutes. Proper maintenance means: listen for changes in sound, Monitor vibration, check temperature, and replace lubricant at the recommended interval. Regreasing intervals depend on speed, temperature, and environment. A rule of thumb is every 3,000 operating hours for standard conditions.